Welcome to S Chemistry. I am your instructor Dr. Suhas Gaudi and today I will be teaching BSc 5th semester Physical Chemistry course on colligative properties of dilute solution. Here is the outline. First, I will go through determine the molecular weight of non-electrolytes followed by abnormal molecular weight of electrolytes, then relation between Van't Hoff factor and degree of dissociation of electrolytes by colligative properties. So let's start with non-electrolytes. So how we can determine the molecular weight of non-electrolytes? So before going to this topic, we will see what is meant by electrolytes and non-electrolytes. So as you can see in right hand side, one beaker is there. So inside beaker, three positive ions and three negative ions are there. So this is dissolved in water. So these two ions are completely separated. So it's a fully dissociated in water. So this is the example of strong electrolyte. So example of strong electrolyte is sodium hydroxide, sodium chloride, and hydrochloric acid. So these are the examples of strong electrolytes. Now we will see what is meant by weak electrolytes. So as you can see in this round bottom flask, two ions are together and one is dissociated. So we can say it is a incompletely dissociated in water. So these ions are incompletely dissociated. For example, is water. Water itself is a incompletely dissociated. Then acetic acid and ammonia. Because of this weak acid and weak base, so this is the weak electrolyte. So these are the weak electrolytes. And third example is non-electrolytes. So as you can see in this round bottom flask, so none of these ions are dissociated. So they do not dissociate in water. So best example of non-electrolytes are sugar, second alcohol, and oil. So these are the non-electrolytes, example of non-electrolytes. Now we will see what is meant by non-electrolytes. So as the definition suggests, non-electrolytes are covalent substance which furnish natural molecule in solution. So they in solution they remain as a natural form, and their water solution do not conduct an electric current. So whatever the solution is there, it will not conduct any electric current. So that is the example, or that is the substance of non-electrolyte substance. So what are the examples? So best examples are sugar, alcohol, and glycerol. So these three are the best example of non-electrolytes. So from colligative property, as we know that colligative property is directly proportional to the how many number of solute particle present in the solution. So as the number of solute is increase, particle increase, so your colligative properties will also going to be increase. So now you will see various types of electrolytes. So the various electrolyte get ionized and yield more than one particle per formula unit in the solution. Suppose you added sodium chloride, after addition in water it will get dissolved into the sodium plus and chloride minus. So it get ionized, and that's why you are end up with the more number of particle. If you add one, you will get two. So therefore the colligative effect of an electrolyte solution is always greater than that of the non-electrolyte of the same molar concentration. So it will be always greater than 1. So by applying this definition, I equal to, that is I to the freezing point depression, we have I equal to delta Tf divided by delta Tf naught. So this will become equation number 1. So here where delta Tf is a freezing point depression for the electrolytes measured experimentally. So this is measured by experimental value of electrolytes, and delta TF is the corresponding value which is calculated for the non-electrolyte substance. So non-electrolyte means, suppose you can take as a sugar, and electrolyte you can take as a sodium chloride. So you have taken sugar 1 mole and 1 mole of sodium chloride, so you can compare this equation. So for that you can check the freezing point of how much freezing point depression will come for the sodium chloride, and this is will be the same molar equation for the corresponding value we can calculate for the freezing point of freezing point depression for the sugar. So in that way you will get the equal concentration. So in other word, delta TF is the value of depression of freezing point of the electrolytes solution assuming no ionization. So in that case we have to assume that there will be no ionization. Now if you equate if you take that into the right hand side, you will get delta TF equal to I into delta TF naught. So from previous lecture we can recall that delta TF naught, that we got this equation number 2. So that is equal to the 1000 into Kf into small w divided by uh, small m into capital W. So if you put this delta TF naught value over here, you will get this equation number 3. So that is delta TF equal to iota into 1000 into Kf into small w divided by small m into capital W. So this will become equation number 3. A similar relation will hold for the observed elevation of boiling point of an electrolyte solution. So for instead of TF you have to put just TB. So delta TB is equal to I into 1000 into KB into small w divided by small m into capital W. So this will become equation number 4. So the value of I can therefore be calculated from the experimental data as mentioned in 4. So if you know the value of I, so you can calculate the elevation of boiling point. So it has been found that once I is known for the particular concentration of an electrolyte for one colligative property, the same value of I is essentially valid for the other properties at the same concentration. So that is iota is equal to delta TF divided by delta TF naught. So this is equally valid for the delta TB divided by delta TB naught, and that is always equal to the delta P divided by delta P naught. So here for this all equation you will get the final answer pi by pi naught. So this is the constant. So where the in all case the subscript 0 refers in each cases to the effect produced by solute, that is non-electrolytes. So at the bottom it's a non-electrolyte and above top it's a electrolyte. So this will be always refer for the non-electrolyte equation or value. So now we are going to moving to the next point, that is abnormal molecular weight of electrolytes. Now we will calculate the molecular weight of the electrolytes. So why they are saying abnormal, that we are going to see over here. So from the previous equation, equation 2 and equation 3, if you divide equation 2 by 3, so it is evident that delta TF divided by delta TF naught will be always equal to m by m naught, and that will be equal to iota. So or you can represent this small m. If you take this m naught to the right hand side, you will get m equal to I into m naught, where m naught is the molecular mass calculated from the formula, and where m is equal to the molar mass from observed data. So this is observed and this is for calculated. So this is theoretical and this is experimental. So since the value of I is always greater than 1 in the electrolyte solution, so the experimental molecular weight will be always less than that the theoretical value. So whatever the here, it will be always less than this m naught, because m naught if you multiply with a greater than 1 value, so this will be always bigger than m naught. So from this formula you can calculate the molecular weight of the electrolytes. Moving to the next point, now we will see the relation between Van't Hoff factor and degree of dissociation of electrolytes, so by its colligative property. So before going to the relation, first we will see what is meant by Van't Hoff factor. So Van't Hoff factor is denoted by small I, and in right hand side you can see the figure where this Van't Hoff factor is measured the number of particle of a solid from its solution. So we are just checking how many solid particles are there. Suppose take the example of sucrose. If you dissolve in water, you will end up with only 1 iota, that is I value is equal to 1, because there is no dissociation of ions. If you take the second example of sodium chloride, so sodium chloride can dissociate into sodium plus and chloride ion minus, so I value will be, that is for 2 ions. And if you take third example, if you dissolve calcium chloride in water, so you will form 3 different dissociate ions, so there are 3 ions. So this is the Van't Hoff factor. Since the colligative property depends on the number of particles in the solution, so the Van't Hoff factor may be interpreted as the ratio of number of particles present in the solution to the number obtained assuming no ionization. So this equation you can expression you can put in the expression in this mathematical expression. So you will get I equal to actual number of particle, that is here actual number particle is sucrose, and the number of particle for no ionization is here it's no ionization, it's single entity only, here both side 1, that's why I value is 1, and here actual number of particle is 2 and divided by number of particle of no ionization. If there is no ionization you will have 1 value, so 2 by 1 is 2, and here 3 by 1, so here I value is 3. So this is the Van't Hoff factor equation. Now we will move to the next point, that is degree of dissociation. So degree of dissociation is represented by alpha. So the degree of dissociation is the fraction of electrolyte which is dissociated into ions in aqueous solution. So you have electrolyte, so it will be always get dissolved in and dissociate into the ions in aqueous solution. So in that case you will get degree of dissociation. If your electrolyte is 50% dissociated, then its degree of dissociation value will be alpha equal to 0.5. So in that way we have calculate. In that case your Van't Hoff factor will be always greater than 1, because number of ions will be going to increase. So that's why I value will be always greater than 1. So this scenario you can understand by pictorial form. So here scenario 3 type kind of scenario is there. One is undissociated, and here one molecule is dissociated, and here both molecules are got dissociated. So now we are going to see what 3 parameters will be there. So amount of dissociated substance in the first case is 0. So in second case it's only one got dissociated, another is same, remain as it is, and in second case both got dissociated. So that's why here number came 2. If you take in terms of undissociated substance, so in first case it is 2, there is no dissociation. Here only one dissociate, one is undissociated, so that's why only one value come here, and here both are dissociated, so that's why number of undissociated substance is 0. If you consider total number of substances, so you have to just add first and this second row. So if you add 0 plus 2, it will be 2, 1 plus 1, it will be 2, 2 plus 0, it will be 2. So in that way you can calculate the total amount of substances. Now come to the fourth point, that is degree of dissociation, which is represented by alpha. In that case you will come 0 by 2, that is 0, 1 by 2, that is 0.5, and here 2 by 2, that is 1. So highest degree of dissociation will give 1 value. Suppose if you take 1 mole of electrolyte is capable of forming new number of ions on complete dissociation, then you will get the following expression. So if the degree of dissociation can be represented by equal to alpha, then the total number of particles in the solutions are. So number of undissociated molecule will be always 1 by alpha. So undissociated means, so total will be 1 after dissociation, and if you minus 1 by alpha you will get number of undissociated molecules. Now if you want to calculate the number of ions how many produced, so you know the new value, that how many number of ions will be generated. So if you multiply with the alpha you will get the number of ions produced. So what will be the total number of particles? So first line and second line, if you add these two you will get the total number of particles, that is 1 minus alpha plus alpha nu. Hence I equal to this total number of particle divided by number of undissociated molecule, that is 1. So in that case if you take this one over here and multiply, so if you rearrange all this equation, finally you will get this alpha value. So this alpha is equal to I minus 1 divided by nu minus 1. So here I is Van't Hoff factor and this alpha is degree of dissociation. So this expression state the relationship between Van't Hoff factor and the degree of dissociation. So once you get the relationship between Van't Hoff factor and degree of dissociation, certainly by knowing the value of I from colligative property measurement, alpha can be calculated. So from colligative property you can easily calculate the from elevation of boiling point or freezing point, you can easily calculate the value of I, and from I you can certainly can calculate the degree of dissociation. So these are the application of colligative property. So here we come to end of this lecture. These are the references for the images, and left hand side and right hand side is books for referring the above given content. So thank you for kind listening. See you in next lecture. Till then, happy learning.